Hi, welcome to section 7.1, which is our first section in Math 149. We're going to talk about collecting and graphing data today. We're not going to do so much collecting in this video, but we're going to look at a lot of graphs, different types of graphs, and talk about what type of data these specific types of graphs are good at representing, and maybe some pros and cons with each type of graph. So before we jump into bar graphs, which is our first type of graph, I want to just talk about some different types of data that you might want to graph. There's really two main types of data, and those are, we've got our qualitative data. That's Qualitative, qualitative, and quantitative. There we go. Okay, qualitative and quantitative. Qualitative data, that's like your most often like categorical data. So when you're graphing certain categories, for instance, like this first bar graph, teachers can respond, they might favor or oppose or have no opinion in terms of a starting time of school. Quantitative is usually numerical. So if you're graphing like average rainfall for every month in the state of Michigan, for example, that would be quantitative. So think numbers for quantitative, and then categories, that's more like just words that you use to describe different categories. And then within quantitative, we're going to talk about two specific quantitative types of data. One is discrete. And discrete data is usually almost always whole numbers. So for instance, I'll give you some examples. Like if I had polled my students and I had asked them, how many siblings? So number of siblings. If I said, how many siblings do you each have? And I had them, each person in my class answer that question on a survey, they might answer 0, 1, 2, 3. They're going to say, they're going to give me a whole number. They would never say like, I have 3.4 siblings, because that wouldn't make sense. So this is discrete data because there's a specific list of possibilities, and the numbers in between those numbers don't make any sense. The other type is what we call continuous. And continuous can be tricky because sometimes when students see this, they think, oh, that the actual variable itself can go on forever. So for example, I'll give you an example. Continuous variable might be height. And I've had students say, well, height is not continuous. And I'm like, well, why? And they say, well, it's not continuous because you stop growing and you can't grow and grow and grow. It doesn't keep on going, which is true. But when we say that the variable is continuous, we're not talking about the variable itself. We're talking about the numbers that we use to describe the variable. So if we think about the numbers that we would use to describe height, so I would say, well, I'm 5 foot 5 inches, so I'm 65 inches tall. So that's one possibility for height. Now that's a whole number, but let me ask you this. Is it possible to be measured in, with a more degree of accuracy? So is it possible to be 65.5 inches tall? Sure. Is 65.75 inches? Can that be measured? Yeah. Can you measure 65.875 inches? Yes. There are infinitely number of decimals that we can use to measure somebody's height. Same with measuring temperature or measuring time. We can always get in smaller and smaller increments. Now, is it common to do that? No, I mean, it's not common for me to say my height is 65.3256789 inches, but is it possible? Yes. So the numbers that we use to describe height don't have to be whole numbers, so we say that those are continuous. So let's jump into bar graphs. I'm sure you've seen a bar graph before, so this isn't going to be new, but let's kind of talk about some pros and cons and what type of data they'd be good at. And this is a great spot if you want to pause the video and try to, jot down some pros and cons yourself. That would be great. So we've got a couple of examples here. We've got a regular bar graph, a single bar graph on the left, and then there's a triple bar graph on the right. Notice with the triple bar graph, different colors are used. In this case, there's this legend here that describes what each color is representing. Oftentimes you see a legend that's actually on the side where maybe you have a box and it's blue, and that represents 1 to 2 people, and then maybe there's a green and a red box as well. So there's different ways to kind of label a double and triple bar graph, but these are some options. Um, so what type of data are bar graphs good at representing? Well, let's look at the data that we have here. So in this first one, we've got favor, oppose, no opinion. So that's category. So I would say categorical data, which is qualitative. So categorical data, which is qualitative. Okay, I'm using categorical because, you know, the name suggests categories, and I think that's a little bit easier to remember than qualitative, but either one work. So qualitative data. Now, if you look here, we've got years. Now, in this case, years are technically numbers, but I would say those could be also categories too. It's a point in time. I would say you could also graph discrete data. It's totally possible to make a bar graph where maybe you're graphing how many, like my previous example, how many siblings your class has. You know, you could draw your axes and maybe you have 0 siblings, 1 sibling, 2 siblings, 3 siblings, and you graph how many people in the class have each, you know, each response. So this would be number of siblings. So it's possible to also graph numerical data with bar graphs. So pros and cons, this is where, you know, I'm just going to jot down some that I can think of, and this is certainly not an exhaustive list, and I think it also just depends on the person's point of view. But pros, some things that my, you know, students have said before that they like about bar graphs is that they're easy to read and understand. Part of that may be because they're common. They're common in American school, K through 12, so maybe it's easy to read because you've seen them before. I've also heard students before say that they're difficult to sometimes read if there's not a grid. So for instance, like this graph on the right here, if I wanted to read this, you know, green bar here, I'd have to come over. See, my line isn't very straight, but if I used a piece of paper or straight edge, I could see that it's 8. Sometimes though, it's hard because if the bars aren't landing on exact whole numbers, it might be hard to read, you know, read bars that have numbers associated with them that are not whole numbers. So hard to read decimal values if there's not a grid. If there's grid, that makes it a little bit easier. Some other pros, I think you can make a quick conclusion. So quick conclusion. Whoops. Help if I could say spell conclusion. Conclusion, there we go. You can make a quick conclusion just by looking at it. So if I look at this first one, I can easily see, oh yeah, most teachers said favor, and then fewer said oppose, and then the least was no opinion. So it's pretty easy to look at, you know, conclusion. You can see trends very easily. So if we looked at a bar graph with maybe, you know, I don't know, rainfall over time, and you see it going like this, then you can see, oh yeah, it's decreasing. Now you have to be careful with the scale of the axes because it's really easy to adjust the scale and make graphs look, you know, deceiving. So just something to look out for. A pro they can be really good for big data, because you can make the axes anything in increments of anything you want. So maybe you have really big numbers to graph. You know, it wouldn't be that big of a deal to graph large numbers because you could just change the scale of your axes and make that and change it so that, you know, you don't have to graph a gigantic bar. Let's see, any other cons other than maybe it's hard to read decimal values, hard sometimes to read if there are no grid lines. Might be another one. And there's other things here that I'm not mentioning, but those are just a couple. So let's jump into pie graphs. What type of data are pie graphs good at representing? So pie graphs can't graph everything. I mean, there's some data where it just probably wouldn't make sense. So take that rainfall example. If I wanted to graph the rainfall in Michigan every month of the year, it probably wouldn't make sense to do a pie graph. Although, you know what, now that I think about it, I guess if I was just looking at a year, maybe I could and do a pie for every, or a slice of pie for every month. Although that would be a lot of slices. That'd be 12 slices in a pie. But say, for instance, I wanted to graph rainfall over 5 years, it really wouldn't make sense to do a pie graph because that would be way too many slices. You couldn't even be able to tell which one's which. So I think they're good at representing data that's part of a whole. So data that is a part of a whole, and categorical data that has limited number of categories. And I'm saying this because you just don't want too many slices. It gets to the point, and I'm sure you might have seen these before. There's tons of really good examples of bad pie graphs out there where, there's 20 slices of the, in the pie, and you can hardly even tell which one's which. So you don't want too many. And I don't think there's a specific number where, a cutoff, but I think as long as you're able to read the graph, then that's a good indication that you have a good number of categories. Some pros of pie charts. I think that they could be persuasive. So you can look at them like if maybe this is an example of the teacher responses and changing hours of the school day. So you can look and see, oh yeah, favor, that takes a big chunk. I can easily look at that so it's quick to draw conclusions. And I said that about bar graphs as well. I can easily say that this category has the most, and this is the fewest. Okay. Everything is relative to the whole. And what I mean by that, like in this example with teachers, I'm looking at all of the teachers. So the whole in this case would be this group of teachers that I'm surveying. Or maybe I do a pie graph with my class and I graph their favorite type of meals. So I give them, maybe 5 choices. Like, do you like Italian? Do you like, Mexican food? Do you like American food? Do you like barbecue? And then they're answering those questions. And my whole is the class. And then each part is the different types of groups of food there. So some cons with a pie graph. I think it can be misleading, and this is a con really with any graph. I mean, any graph can be misleading, but specifically pie graphs, like I'm looking at this teacher example, 45% of how many? How starts with W or H? How many? There we go. So for instance, like, maybe I only surveyed 8 teachers. I mean, that's not that many teachers. It probably doesn't warrant a pie graph. Maybe I surveyed 1,000 teachers and it makes more of a difference. Well, 45%, it'd be nice to know 45% of how many. So it'd be nice to know the actual number of teachers. And that's just a con with this one. One other thing that I think is a con or could be a con is that they're a little bit more time consuming. So you have to calculate the number of degrees of each piece. So it's a little bit more work if you're not using software. I mean, we've got all kinds of good software now. I mean, Excel can do one of these in, less than 5 minutes if you want it to. But if you were going to do this by hand, you'd have to calculate the number of degrees of each piece. And I'm going to actually show you how to do that. So I'm going to erase these. And I'm going to list each category. So I'm going to list favor. And I'm going to list oppose. And then I'm going to list no opinion. And what I'm going to do is I'm going to look at I'm going to try to find the central angle degree, which is this degree measure right here. So this is called the central angle degree. So if you need to calculate the degree measure of the part of the circle or each piece of the pie, these are the steps that you would use. So to calculate the central angle degree. So the first thing we're going to do, step one, is we're going to make a fraction of, and I'm just going to draw a line here. We're going to make a fraction that represents the part and whole, if we can. The next thing we're going to do is we're going to write down the percent, and the last part is we're going to write the decimal there. So those are the three different options you have in terms of calculating the central angle degree. So in terms of the fraction, you need to know the specific numbers. And in this case, in the pie chart, I actually, in this first pie here, I don't have the specific number of teachers. Now, if I scroll up, I actually can get the number of teachers by, this is the same data that's represented in this bar graph above. And so one thing I could do is I could read these bars here and just see, okay, there's 18 people that favor it. Looks like there's 14 people that oppose it. And it looks like there's 8 people with no opinion. And if I add that up, I get 40 altogether. So I could come down here if I had that information in the pie chart. So I'm just going to go through it as if I did. So that way you can see how you would do that. So favor, we'll say there's 18 people that favor, there's 14 people that oppose, and then we said that there were 8 people with no opinion. So for the fraction, what I would do is I would write 18 over 40. For oppose, it'd be 14 over 40. And for no opinion, it'd be 8 over 40. Now, if you want the central degree, angle degree, all you have to do is multiply that fraction by 360 degrees. And that would give you the number of degrees you would need for the piece. You could also do the same thing with the percentage. So in this case, favor is 45%, and we've got oppose is 35%, opinion is 20%. So I can just write the decimal of that percentage, so 0.45, and multiply that by 360. 0.35 times 360, or 0.20 times 360. Now notice the fraction here, 18 over 40, is 0.45. So these are, I'm doing the same thing in each column. I'm just looking at a different type of number each time. So in general, you want to multiply the fraction, the percent, or the decimal by 360 degrees, because there's 360 degrees in the circle. And when you multiply that, you're going to get your degree measure. So when you do 0.45 times 360, you end up getting 162 degrees. So that matches up with this degree measure. And then 0.35 times 360 is 126 degrees. And then with this last one, you end up getting 72 degrees. And if you add those up, so 162 plus 126 plus 172, you should end up getting 360 degrees total. Now, if you end up rounding these, sometimes it's necessary to round because you don't get an exact degree measure. It's possible that your total is really close to 360, like 359.9, and that's okay. I think, when you round, sometimes your answers are off just a tiny bit. So what would you do with this? Well, if you had a protractor, now you could draw a circle, and you could use a protractor to figure out how big of a section you would need for each one of these categories. So that's how you would draw a pie chart if you didn't have software. And this is important for elementary school teaching, because this is something that, we have kids do in elementary school, likely around 4th and 5th grade, where they start to really use a protractor a little bit more. Okay, so let's scroll down and take a look at our next type of graph. So our next type of graph is called a pictograph. I'm sure you've seen this before. So we start in kindergarten showing kids pictographs, and a pictograph is just a graph using pictures to represent an amount of some category. So what type of data are pictographs good at representing? Well, let's look at these examples. So this first one, we have different types of apples. So that would be categorical data or qualitative. And then we've got different types of colors. So favorite colors for students. And then we've also got this one with collecting fruit down here. So all of these are categorical data, which is also qualitative. It is possible to represent quantitative data as well. You know, like how many people, I don't know, maybe heights of students in the classroom, or maybe graphing the number of siblings people have in your classroom. You going back to my previous example. So categorical data or discrete data. I'm saying discrete because remember, discrete data, we usually use whole numbers, so that would make more sense. Now I did say heights. You could do heights, but I think if you did, you would have to probably round, like how many people are around 60 inches tall, or how many people are around, you know, 50 inches tall. Because you're not going to want to get into all of those different decimals. I think it would be too confusing with Pictograph. It wouldn't be the best use of this type of graph. So, so what are some pros and cons? So you could stop the video and list some that you think. I know when I talk to students in class about this, the pros that come out are that it's fun for kids. So kids like to do these because they can use, you know, pictures in different shapes. It's easy to read. I think it's easy for counting, especially for those younger grades where they're really working on that one-to-one correspondence, and they can actually put their finger and count, oh yeah, there's 1, 2, 3, 4 bananas, or there's 1, 2, 3, 4 apples. So that's easy to count. You know, you can actually put one finger on each item, as opposed to a bar graph is a lot more abstract for little kids. So easy to count, so good for younger grades. So what are some cons? So I think it can be misleading, and we're going to take a look at this graph right here. So what could be misleading about this graph? Like if I showed this to my kindergarten daughter and I said, which fruit is there the most of? I would bet that she would say bananas. And she might not. I mean, she might actually count and say, oh, there's 4 bananas, 4 apples, they're the same. But my guess is she would look at this and see that the bananas looked a lot bigger. So there's got to be more bananas. And that's where it can be misleading. So you want to be really careful. So I'm just going to put a note here. Always use the same size for all icons. And I think it's probably best to even just stick with one icon, like this first graph where we just use apples or we just use smiley faces. But I think it's okay to use different types of fruit, but they need to be the same size. Otherwise it's too misleading. It looks like there's fewer apples than there are bananas when there really is not. So it can be misleading. I think it's hard to represent fractions. It's not horribly difficult to cut something in half. Like you can see there's a half a smiley face up here, it looks like, or no, that actually looks like maybe a third. So they tried to, but see, there's where it gets difficult because you're looking and trying to figure that out. I think, you know, here it's very clear with the legend that that's 5 apples. But if you divide it anymore, I think it would get tricky. So hard to represent fractions. I'm also going to put big data possibly. Now, your icon could represent a really big number and make that easier to represent big data. But if the data was really spread out, like you had smaller numbers and then gigantic numbers, it might be difficult to use a pictograph there. So, but I think the key here is that it's really good for younger kids, and it's just a fun way to display data if you're looking for fun and something that's good for younger learners. All right, so let's talk about line plot. So line plot is something that's introduced usually in first grade. I remember when my kids started doing a line plot, and they struggled with it a little bit, especially with the answering questions part. So a line plot is different than a line graph. So I'm just going to make a note. So different than line graph, and I'm just going to do a quick sketch. We'll get to this later, but a line graph would be where you have something like this, where it's two-dimensional. So there's an X and Y. A line plot only has one axis. So there's one line at the bottom, which is a number line. So one number line as opposed to an X and a Y. And then usually X's or dots, they don't have to be X's. It could be dots that are stacked up like this, or X's, or sometimes shapes. Sometimes these are combined with pictographs. But what type of data are these good at representing? I would say most often discrete data. So we can see here kid height in inches. It's funny because I keep coming back to this height example. So height technically is a continuous variable, but it depends. I mean, if I were to survey kids and just say, okay, pick one, are you 43? If I gave them whole numbers to choose from and they were just to pick which whole number they were closest to, then it sort of makes that data discrete. So it wouldn't make sense to have an option of 43.1 and 43.2 and 43.3 because it would be really tricky to make all of those X's in between. So you really kind of want to stick to whole numbers here. So what are some pros? I think it can be easy to fill out for smaller data sets. For smaller data sets. It can be a total pain if you have big data. So cons, it's not great for big data. So if you had a class of, 2,000 kids and you wanted to plot their heights, by hand, that would take forever. I would say it's good for younger grades. This is a really good one where maybe in first and second grade you have kids survey each other. You pass out a survey and you say, all right, go around and ask your classmates how tall are they, or they might not know how tall they are, but maybe you can ask them, how many siblings you have, and they fill out a little chart and then they go back to their seat and they do a line plot. The other nice thing is that there's an X. It's that one-to-one correspondence again, where they have one X per person and then they can count and make sure everybody in the class is accounted for. So I'm just going to put one-to-one correspondence, which makes for easy counting. It can be tedious, for sure, but I think when we're just starting with graphing with the younger grades, I think it can be good. Oh, and you know what else I forgot? Pros, I'm going to say it's easy to spot high and low points. So it's easy to look at and be like, oh, there's a clear winner here. There's more people that are 53 inches tall because you've got that high point. So the next one, stem and leaf plot, we definitely don't get to until either later elementary school or even middle school. Sometimes teachers won't even do this in elementary school. I know when I was taking my teacher certification test for math, which is which was 6 through 12, so it was secondary. This was the one question I got wrong on my test because I had never even seen it before. I never saw it in K-12 school, and I never saw it in in college, but it's not too bad. It's pretty simple when you know how to read it, but it's definitely not the most intuitive. Why are we doing it? Well, a couple of reasons. One, mostly just because it is possible to see this in elementary school curriculum, so it's a good thing to mention, and it does have some pros. So let's talk about how to do it, and then we'll talk about pros and cons. So what we're going to do here is you're going to make a T-chart and you're going to write stem on one side, leaf on the other. So this is already done for you. And then the next thing you do is you fill out what we call the stems. Well, the rightmost digit is always the leaf. The rightmost digit is always the leaf. So you have to look at the types of numbers you're given. So in this case, it looks like I've got numbers. I'm just going to write down the smallest one. So it looks like the smallest one is 45. I've got numbers from 45 all the way to, looks like 95 is my biggest value. Yeah, so 95 and 45. So 45 to 95. So my rightmost value in this case is going to be the ones place, and then the leftmost is going to be the tens. So we're going to call the stem is going to be the tens place, and the leaf is going to be the ones place. Now, if you had larger numbers, so say for instance you had numbers in the hundreds, like 123, the the 3 is always your leaf, and then whatever's left is going to be your stem. So in that case, you would actually have stems that maybe are 12 or 13 or 14, and that would represent numbers in the hundreds. So the next thing you're going to do is you're going to group the data into each STEM category. So the 4 represents 40s. So I'm just going to list out all the numbers in the 40s. So I'm going to go through and actually, you know what, why don't I do it this way? I'm just going to write 40s, 50s, 60s, 70s, 80s, 90s, and you can sort this using a graphing calculator. You could even use Excel if you wanted to, but for this first one, I'm just going to go through and do it by hand. So I'm going to go through the data, 82, and I'm going to put it in the category. So that'd be in the 80s, 66, 60s, 70s, 77, 94, 67, 73, 78, 82, 74, 90, 45, 62, 85, 57, 72, 94, 83, 85, 70, 95, 71, 89, 87, 75, and 74. Okay, so and then I would double check and count everything. I've got an answer key. I'm just comparing right here, and it looks like I've got everything, but I would definitely count, make sure you've got all the numbers. You should have 26. And then you start with the first stem, which is 40s, and you're just going to write down a 5, and that represents 45. Okay, so we're done with the 40s. And then 50s, so 57. Okay, those are easy because I only have one number. With the 60s, you have to put them in order. So the 62 is going to go first. So you're going to write a 2, and then a 6, and then a 7. And I know it seems weird. I always want to put commas, but you're not supposed to put commas. So this represents 62, 66, 67. Okay, so 62, 66, 67. And then so we're done with 60s. And then 70s, I'm going to go ahead and list those. So it looks like I've got 2 70s. So I write 0, 0. So a 0 means you actually have a 70. If for some reason you didn't have a value, like any 70s, you would just leave that row blank. So if you put a 0, it means you actually have that number 70, not that you don't have a number there. So two zeros, and then it looks like I've got a 71, and I've got a 72, and I've got a 73 and a 74, and it looks like I've got 2 74s, another 74, and then I've got a 75, and then a 77, and then 78. Okay, so you can see the nice thing about stem and leaf plots is that you can see that there's this clear winner here. If these are test scores, it looks like I've got a really big bunch of students that are scoring in the 70s. So that makes it nice to, you can quickly see that. So now I'm going to go through the 80s. So I've got 2 82s, so a 2 and a 2, an 83, an 85 and an 85, an 87, an 89. And actually, to make this a really good graph, the best way to do it is really try to make your digits the same size. Like I made these a little bit bigger on this row than the top row because, you know, when you make the digits bigger, it appears like it's a longer row than it is. Kind of like that misleading pictograph we just looked at. So the 80s are done, and then 90s, we've just got 4. So I've got 90, and then 2 94s, and then I've got a 95. Okay, so just to reiterate, the stem in this example is the tens place, but it could also be the ones or the hundreds place or thousands place, depending on how big the numbers are. But in this case, it's just the tens. And then the leaf is always the rightmost digit. In this case, it is the ones. It is possible to use this for decimals. So for instance, if you had numbers like 32.5, the 0.5, that would be your leaf. And then this part would be your stem. So the leaf is not always the ones place. It's whatever place value is the farthest to the right. So So let me just scroll down here. We're gonna do a back-to-back stem and leaf plot, but I'm just gonna well, you know what? Actually, let's do that first, and then we'll do the pros and cons, so that way you guys can see the difference. So with this back-to-back stem and leaf plot, it's a very similar process as before. I'm not going to go ahead and do each category, but I'm just going to show you how it would look. And this would be one if you want to I'll explain it first, and then if you want to go ahead and stop the video and do it on your own and then check your answer, that would be helpful. So for a back-to-back stem and leaf plot, you're gonna, just like above, we had a stem column and a leaf column. Well, now we're gonna scroll back down. Sorry about my scrolling. I'm used to a MacBook and I'm on a PC, so it's scrolling the opposite way that I'm used to. So our stem is going to go in the middle, and we have two leaf columns. So we've got the leaves on the left and leaves on the right. In this case, I've got my class 1 and class 2, so I'm going to actually label it that, class 2 and class 1. You could write it leaf 2, leaf 1, but it makes more sense to just label it whatever category if you're given the type of category, the description, and the problem. And so for class 1, you're going to go ahead and I'm going to write the same stems as I had before. And the reason I'm okay doing that, I'm just looking at the class 2 data, and it looks like those numbers are in the same range as I had for my class 1. So if for some reason I had a value like in the hundreds, then I'd go ahead and add a 10 into the stem. But I think I'm pretty good sticking to 4 through 9. So then with class 1, you're actually going to just copy down the same stem and leaf plot, all those numbers that we just did from the previous example. Okay, and then for class 2, the tricky thing with class 2 is you actually have to work backwards. So we're going to go ahead and find the 40s, and it makes sense to put these in categories like I did above so you don't miss any, but we only have a 49, so you're going to write 9. And I know it's so weird to read right to left because we never do it, but in this case you have to. So the stem is 4, and so this reads 49 that way. And so with the 5, it looks like we have a 52 and a 55. So here's a 55 and a 52. You actually have to order it so where the lowest number is closest to the stem. So the 52 is going to go first and then the 55. So it's ordered from least to greatest, working from the stem outward. So this way and then this way, depending on which side you're working on. So we've got 52 and 55. And then the 60s, so I go ahead and I'm just going to circle all of my 60 values, and then I'm going to go ahead and put those in order. So I've got a 63, and I cross that off. I've got a 64, and I cross that off. I've got two 66s, so 66 and 66. I've got a 67, and then I've got two 68s. So it's going to look like that. And then for 70s, I've got lots of 70s, so 79. Okay, and I'm going to go ahead and just fill those in. So I've got a 70, I've got two 71s, I have a 72, a 73, 73, 75, 76, and then I've got a 77. I'm going to go ahead and just cross these off. And then I've got a 79. And I would obviously be going a lot slower if I were doing this on my own, but I'm just trying to show you just the big picture here. You can pause the video and work on this yourself if you want to go a little bit slower. So for 80s, I'm going to go ahead and I've got an 81 and an 82 and an 84, an 85 and an 89. So I cross all those off, and then it looks like I've got 190, I've got a 91, and then we put that there. And so what this does is this allows us a really good visual of how to compare class 1 with class 2. So so what are some pros and cons with this stem and leaf plot? So I would say the pros is it's easy to see high and low categories. or high and low areas. So in this case with the test scores, I can see that these classes really scored a lot in the 70s, and then we've got some 60s and 80s there too. Those were the clear winners. And I think, I think it's pretty simple. I think the back-to-back, is definitely more complex. The cons, it can be tedious. It can be difficult to read if you don't understand how to do it. For sure. I'm going to say for the average person or somebody that just hasn't been in a math class for a while, or like me, I had never even learned this, so it was very difficult for me to read it. And I think it can definitely be hard to read from right to left, as in like with the class 2. I could see how somebody might read this as 94 instead of 49. But yeah, so that's the basics of a stem and leaf plot and a back-to-back stem and leaf plot. So let's go ahead and talk about a histogram. So a histogram is really useful when data is spread over a wide range with many different values. And when that's the case, it's helpful if you group the data into intervals. So anytime you have data that's graphed in intervals, that can be helpful. So in this case, I'm going to actually use the data that we just went through, and we're just going to use, we're going to call this class 1 data. So above, when I graph those two classes, in fact, I'll just scroll up real quick. There we go. So you can see class 1. What we can do is we can group this data into intervals. So for example, how many scores were there between 40 and 49? And we're just looking at class 1. So, and actually, what I'll do is I'll just even erase class 2. So we'll just look at the regular stem and leaf plot here. So that way it's super clear. And actually, let me go. That's 4, 5, 6, 7, 8, and 9. And there's my stem. Okay, so it looks like there's one score, 45, in that category. There's one score in the 50s. There's 3 scores in the 60s. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, it looks like, in the 70s. So 10 and 80s, 1, 2, 3, 4, 5, 6, 7. And 90s, we have 4. And so then what you can do when you graph, it looks a lot like a bar graph, only the bars touch each other. So bars touch. Okay, and usually in this case, I'm going to start my x-axis at 0, and the score, I'm going to graph the score on the x-axis, and then frequency is going to go on the y. And with histograms, frequency is always on the vertical axis. So my largest frequency is 10. So I'm going to just make my intervals so that way I can fit 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5. Okay. And then I'm going to make my intervals. So I've got 40 to 49. And you know what I can do actually? I'm going to erase this, and I'm just going to do a little squiggly line, and what that represents is that we are going to jump, and instead of starting at 0, I'm just going to start at 40, and I'm going to end at 49. And then my next one, actually, you know what? I'm going to label this 50 here, and I'm just going to use these numbers on the left. So 40, 50, 60, 70, 80, 90, and if you want, I'm going to go one more to 100. And if you want to write the range in there, like I started to do that, 40 to 49 like this, you can. It's just a little bit more writing, and it's kind of scrunched. So what you can do for the 40 to 49 is you actually bring the bar all the way to 50, because it just stops just shy of 50. And then we'll start the next one right at 50, and that's also going to be 1. So actually here, what I should do is get a different color. So that way it's clear that these are separate. There we go. And then from 60 to 69, I have 3. And then from 70 to 79, I have 10. And then from 80 to 89, I have 7. Whoops, I did not want to erase that. So 5, 6, 7 looks like there. And then 90 to 99, it looks like I've got 4. Okay, so that's what a histogram would look like. So the bars touch each other because where one interval ends, the other one begins. And so if it bothers you to have 40 to 50 when you know it should be to 40 to 49, you can, like I said, make that range there. Pros of a histogram, I think it's nice. It's a really nice way to graph ranges of data, and it's a really good way to see highs and lows. So just like that stem and leaf plot, like where are there peaks, or are there more than one peak? You know, it can be time consuming because you need to do a frequency chart first, but when you're done, I think, you know, it's a good way to display data. You can see, as I noted here, there is an example in the book where there's a larger range if you want another example of a histogram. Okay, so a couple more examples here. So we've got line graph. We're going to talk about line graph and then scatter plot, and then we're done. So this is the last page of the 7.1 notes. So a line graph is different than a line plot. So just remember, just jog your memory. Line plot, we talked about this one, is where you just have a number line and you've got X's or dots that represent amounts of each data value. With a line graph, it's a two-dimensional graph, like you can see, and lines are connected, or I'm sorry, points are connected with line segments. It's really useful for changes over time. So you can see in this example, this is population growth in the United States. You can see over time that connecting those dots really helps us see that pattern there. This is in contrast to down below where we see a scatter plot. Now, it's tempting to think that a scatter plot is just a graph where plots or points are scattered all over the place. They're not necessarily scattered. So a scatter plot is just a graph of ordered pairs. So we've got an X and a Y. In this case, we're graphing height versus shoe size. So 2 variables. And that's the same case in this line graph. We're graphing 2 variables in this one as well. In this graph, we're graphing the year and the population. So in this first one, dots are connected, or I should say points or ordered pair, not connection, connected. And in this second one, the ordered pairs or the points are not connected. And that's the real difference between a scatter plot and a line plot. I could graph this graph up here. I could graph each of these points and just not connect the lines, and I'd still call it a scatter plot. Typically with scatter plots, what we do is instead of connecting the line or connecting the points, because that doesn't oftentimes make as much sense, because in this case, if I were to connect them, they're sort of, you know, they don't connect very well unless you're doing one of those art things where you're connecting it to make a picture. But typically what we do is we do what's called, we draw what's called a trend line. And a lot of times we use a graphing calculator or computer software to do that. We're not going to do that in this class, but I'm just going to touch on this briefly. To make a trend line, what you would do, like in this class, if you're asked, like in your homework, for example, there's a problem that I believe asks you, you're graphing the points and then you have to graph a trend line. In this case, you would just take a ruler and you would try to graph or draw a line that goes through as many points as possible, or is as close to as many points as possible. It actually might not go through any points. But if I were to just kind of, I don't have a ruler, but do the best job I can at drawing a straight line that minimizes the distance between the points. So every single point has a distance to the line, and what graphing software does is it just tries to minimize that distance of all of the points so that that line can be as close to those points as possible. Sometimes you'll hear this be called a line of best fit. And there's a couple of different types of trend lines that you might see, and we're going to touch on those here. So we've got an example here where we have a positive correlation because the line that's drawn here, the trend line, has a positive slope. It increases, it goes up from left to right. With this last example, we have a negative correlation, which means there's a negative slope. And to interpret that in terms of the data, it just means as something is increasing, so as our x variable is getting bigger, the y variable is getting smaller. So, we could, make up an example, like think of something, maybe something in your real life where, as you do more of something, maybe something else goes down. So I don't know, maybe the more you exercise, the less someone weighs. Now, granted, that has a lot of variables other than those two things, but that's just, a silly example. Or maybe in this example in the middle, the more you study, so hours you study, your grades increase. So the more you study, your grades increase. We can say that there's a correlation there. There's a correlation between ice cream sales and shark attacks. This is true. So the more shark attacks, or I'm sorry, the more ice cream that's sold, that's related to an increase in shark attacks. Now, just because there's a relationship there doesn't necessarily mean that it's a causal relationship. So that doesn't mean that the more ice cream that's eaten in the world causes more shark attacks, but they could be related maybe by something else. So maybe weather, maybe when it's warmer outside, there's more ice cream eaten and there's more shark attacks. And so it's easy for anyone to throw that in a graph and say, oh, look, there's this correlation, there's this positive relationship, but it doesn't necessarily mean that one's causing the other. So I do want to just briefly mention, so graphing calculators in computer software can give us, it's called a correlation coefficient, and it tells us how strong of a fit this line is. So, and the way that it's done is we say that a 1 is a perfect positive fit, meaning the line is going up from left to right, and it literally is going through every single point. If it's a -1, if the correlation coefficient is -1, then we say there's a perfect negative fit, and that means the line is going down from left to right, and it's literally going through every single one of the points. Now, in these examples up here, I would say, like, if I had to put a number to this last example, okay, so it's negative, I would say that the correlation coefficient, I don't know, maybe it's -0.85. It's definitely not -1 because it doesn't go through all those points. I would say that it's closer to 1 than it is to 0 because it looks like it does a decent job of fitting, but the points aren't, they're not super close to the line. And maybe I could say that this one is a positive 0.85 because it's going up from left to right, and it's, it's not a perfect fit, but it looks pretty decent. And then this first scatter plot, it would, if you ask computer software, it would give you a correlation coefficient there, but it's probably going to be closer to 0 since those points are scattered all over, and they do not look like they go up in any type of line shape. So, so that's it for 7.1. I hope that made some sense. As always, just let me know if you have any questions.